So 3 days ago, we talked about homogeneous ODEs. To completely solve a homogeneous ODE, all that we needed to do was find linearly independent solutions. How many did we need to find? Well, it depended on the order of the differential equation. Second order, we needed 2. Third order, you would need 3. Fourth order, you would need 4, etc. We saw that the reduction of order technique gave us a way. If we had one solution to a second order differential equation, we could construct that second one that we needed to get all possible solutions to the ODE. But then the question becomes, okay, well, where do we get the first solution? And we're going to get started talking about that over the next couple of days. Once again, with differential equation, there are really only a handful of problems that we can actually really solve using exact methods, as opposed to the numerical methods like Euler's method or RK4. So we're going to focus in on a few of the more important types of differential equations that we actually know how to solve. And the first of those is a homogeneous equation with constant coefficients. So a homogeneous equation with constant coefficients is just a homogeneous equation where in front of all the derivatives of y, we just have constants there. Alpha sub n times the nth derivative of y, alpha sub n minus 1 times the next derivative down to the first derivative of y times a constant, plus a constant times the 0th derivative, the original function. The only difference here is that non-constant functions of x are not allowed. These all have to be real numbers. So some examples of homogeneous equations with constant coefficients. Both our spring mass equation and our RLC equation were homogeneous with constant coefficients. Unless the mass of your spring was varying over time, unless your inductance, resistance, and capacitance are changing over time, these two equations represent examples of homogeneous equations with constant coefficients. So the techniques that we introduce today and tomorrow will be applicable to problems like these in real-world applications. Now, the technique for finding solutions to homogeneous equations with constant coefficients is to once again sort of go in with an educated guess. You're going to guess that a solution has the form y equals e to the r times x. Where does this guess come from? A whole lot of research by a whole lot of very intelligent folks over a long period of time. We tried it, and hey, it just works.
All of this just works. It just works.
Guess this solution, plug into the ODE, simplify as much as you can, and then try and solve for r. Now when you do this, in step number 2, after you've simplified as much as possible, you're going to end up in step 3 with an equation that looks like a polynomial in the variable r. And this polynomial has a special name. It's going to be called the auxiliary equation. So you'll hear me refer to the auxiliary equation from time to time. In today's video, we're going to focus on the case when the auxiliary equation has distinct real roots. I've said 2 here, and I really shouldn't. When the auxiliary equation, when you solve it, there are completely distinct real values of r, no repeated values of r, and no complex values of r. Let me show you what I mean. Let's solve the differential equation y double prime minus 3y single prime plus 2y equals 0. First, let's acknowledge that this equation is homogeneous with constant coefficients. All of the derivatives are being multiplied by just numbers. Y double prime is multiplied by 1, y single prime by negative 3, and y with no primes by positive 2. So I'm going to guess that a solution has the form e to the rx. And I'm going to then figure out what y prime and y double prime would be based on that guess. Well, y prime, a single copy of r would come down. Y double prime, 2 copies of r would come down. And if I plug that into the equation, I get r squared e to the rx minus 3r e to the rx plus 2 e to the rx. Now notice that all 3 terms contain an e to the rx. And since that can never be equal to 0, it can be divided out, leaving me with just the polynomial r squared minus 3r plus 2 equals 0. This is our auxiliary equation. This is the polynomial which contains just the variable r that we can solve for r. This one's simple enough that we can actually solve by factoring, it looks like. It looks like r is either equal to positive 2 or r is equal to positive 1. In either case, our function y equals e to the r times x is a solution. So by making this guess, we've actually obtained 2 solutions. One which is e to the 2 times x, and another which is equal to e to the 1 times x. Now you can confirm, but different r's give linearly independent solutions. If you just want to check this, we can have a quick look at the Wronskian. If I fill up this 2 by 2 matrix with the original functions and their derivatives, and then calculate the determinant, I get e to the 3x minus 2e to the 3x, which is negative e to the 3x, which is not 0. So the Wronskian confirms that these 2 functions are linearly independent, and as a rule, different r values will give you different solutions which are linearly independent. So having found 2 linearly independent solutions to this second order homogeneous ODE, the general solution then must have the form y equals c1 times the first solution plus c2 times the second solution. Every solution to the ODE must be equal to something of this format. Okay, what about if we had y double prime minus 4y prime plus y? If I guess y equals e to the rx, once again y prime brings a single r down, and y double prime brings 2 r's down. So I get r squared e to the rx minus 4r e to the rx plus e to the rx equals 0. And once again, that e to the rx can be divided out. Now this equation cannot be factored, but that doesn't mean it can't be solved. It just means we might need to bust out our good old friend quadratic formula.
X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a.
So this looks like 4 plus minus root 12 over 2 which I think simplifies to 2 plus minus root 3. So the two values of r given here correspond to our two solutions. One with the positive square root, e to the 2 plus root 3 times x, and the second solution corresponding to the root with the negative sign. Different r values, so we have linearly independent solutions, and therefore our general solution is C1 times solution number 1 plus C2 times solution number 2. So that's all well and good for second order homogeneous ODEs, but this trick can even work with ODEs of a higher order, such as third or fourth or fifth order, as long as they have constant coefficients. Now, here's a theorem that can be helpful in such situations. Before I finish writing down the conclusion of this theorem, I actually want to skip ahead a little bit and show you a situation that might motivate this theorem and explain why it's going to be useful. So someone asks us to solve y triple prime minus 7y prime plus 6y equals 0. So this is going to be a third order homogeneous ODE with constant coefficients. We're going to make our usual guess, which is going to have its usual consequences. Y double prime has 2 r's come down, so y triple prime has 3 r's come down. And therefore our differential equation becomes r cubed e to the rx minus 7r e to the rx plus 6 e to the rx equals 0. And after canceling out the e's, I'm left with this degree 3 auxiliary equation. Now, because this is no longer quadratic, we can no longer solve this using quadratic formula.
X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a.
So what are we going to do to be able to determine the values of r that make this equation true? That's where the previous theorem comes in. It gives you a way to sort of make an educated guess about the values of some of the solutions to an equation like the one below. If you have a polynomial whose leading coefficient is 1 and all the other coefficients are integers, then the integer solutions to polynomial equals 0 are factors of the constant term in the back, a0. If you want to find whole number values which make this equation, make this polynomial equal to 0, try focusing your attention on the numbers which are factors of the constant at the back. So here we want to make r cubed minus 7r plus 6 equal to 0. And the theorem tells us try and guess factors of the number 6 here. So plus minus 6, plus minus 3, plus minus 2, and plus minus 1. We can really just plug them in. R equals 1, for example, if I plug that in, I get 1 minus 7 plus 6, which is equal to 0. And that means that r equals 1 actually is a solution. You can go through the list one by one. That's just arithmetic. So it turns out that the other roots are r equals positive 2 and r equals negative 3. So our solutions to the differential equation have the form e to the positive 1 times x, e to the positive 2 times x, and e to the negative 3 times x. So our general solution has the form linear combination of these three. Now we have been focusing on solving differential equations, but of course it's also possible to solve initial value problems containing differential equations of this type. We're going to play it exactly the same way that we usually do. We're going to start by finding the general solution, the description of all possible solutions to the differential equation, and then we're going to use the initial conditions to narrow it down a little bit. To narrow it down to the one singular solution which solves the given initial value problem. So solve the initial value problem y double prime plus 4y prime minus 5y equals 0, where we require that y of 1 is 0 and y prime of 1 is 2. So, as usual, we guess an equation of the form y equals e to the rx. Now we've done enough of these problems that we have begun to see a general pattern. Once we guess a solution of this format and plug it into our differential equation, the third derivative gets replaced by r to the third power. The second derivative, as in here, the second derivative gets replaced with r squared. The first derivative gets replaced with r, and the y, the zeroth derivative, gets replaced with a term that has no r's in it. So once I've written down my guess, I'm going to go ahead and skip straight to writing down the auxiliary equation based on just the observations that I've made as I've done these problems over and over and over again. And you're also free to skip directly to the auxiliary equation. To note that y double prime is just going to become r squared, y single prime will become just r, and the y will become basically nothing, and only the constant will come to the next line. So r minus 5, r plus 1 is how we can factor the polynomial on the left, which gives us r equals 5 and r equals negative 1. And therefore our general solution has the format c1 e to the 5x plus c2 e to the negative x. This would be our general solution to the ODE. So now let's use these initial conditions to find the specific solution that satisfies our initial value problem. First, let's go ahead and find the value of y prime, which is 5c1 minus c2 and now let's go ahead and plug in our initial conditions. They say when you plug in x equals 1, c1 e to the 5 plus c2 e to the negative 1, then the result of that should be equal to 0. They also say that when you plug in 1 to the derivative, the result should be equal to 2. Now because we have obtained two terms which are exact opposites in the second position here, I'm going to go ahead with method of elimination and add these two equations together. That causes the c2 terms to cancel out, and that leaves me with 6 e to the 5th power c1 is equal to 2. And therefore c1 is equal to 1 over 3 e to the 5th power. So let's plug that back into either one of our equations. I might just pick the first one at random, which says if you take c1 and multiply it by e to the 5th power, which is going to give you just 1/3, because the e to the 5 and the 1 over e to the 5 will cancel. Add that to c2 times e to the minus 1, that's going to be equal to 0. Therefore c2 e to the minus 1 is equal to negative 1/3, and therefore c2 is equal to negative e divided by 3. So having determined those values of c1 and c2, we can now figure out the exact solution which satisfies our particular initial value problem. c1, which is 1 over 3 e to the 5th power times e to the 5x, and then C2, which is negative e over 3, multiplied by e to the minus x. I'm personally a little bothered by the aesthetics of this solution as it is written right now. So for my own sanity, I'm just going to rewrite this a bit. 1/3 e to the 5x minus 5 minus 1/3 e to the negative x plus 1. Just using the properties of exponents to put some of those e's together. Okay, that concludes today's material. We introduced a new type of homogeneous ODE, specifically the homogeneous ODE with constant coefficients. We introduced a technique for finding solutions to a homogeneous ODE with constant coefficients, which was to guess a solution of the form y equals e to the rx. Today we focused on the case when the auxiliary equation had distinct real roots, so that we could build out a complete set of linearly independent solutions so that we could get our general solution. So tomorrow we'll talk about the case when we have complex roots to the auxiliary equation, and we'll talk about the case when one of the roots is repeated.